Thank you very much. Okay, so dear colleagues, I'm Viktor Makarichev, and I would like to present coding improvement in the algorithm discrete atomic compression. Now, digital images are an essential part of our life. They are widely used in many branches of science and techniques. For example, they are used in remote sensing, medicine, security, ecological monitoring systems, agriculture, and so on and so on. And now a great number of digital images are collected, and a huge amount of different data sets should be stored. And for this reason, there is a great problem concerning resources requirements that are required for storing, processing, transferring images, protecting, training machine learning models, and so on and so on. And these are great expenses. And for this reason, the following image processing trends should be considered as very important. So in this research, we consider the following image processing requirements. First, image processing method should provide time complexity reduction. Also, spatial complexity reduction should be ensured. In addition, data protection and privacy enhancing techniques should be provided. And finally, machine learning oriented data format should be ensured. And there is a question. Is it possible, and how can we ensure this combination? It is clear that if we want to provide fast processing, we should pay for this somehow. And also, if we want to provide, for example, high-level privacy protection, we should spend a lot of time. Also, if we need machine learning-oriented data format, we also need some resources. And there is a question: is it possible to provide all these requirements at the same time? And in this research, we consider one possible solution that is called discrete atomic compression. Discrete atomic compression is image compression algorithm that has the following features. First of all, it has linear time complexity with respect to the size of the image processed. Also, it has linear spatial complexity. It means that we need just linear memory expenses, linear with respect to the size of the image processed. Also, this image compression algorithm provides image encryption due to the possibility to vary its structure. Also, discrete atomic compression provides lossy and lossless compression. And finally, as it has been already considered in our previous research, it provides kind of machine learning-oriented data format. It means that machine learning-oriented data format means that data is stored in such manner that it can be used directly in order to train machine learning model or something else. And in this research, we are going to improve discrete atomic compression. Consider this algorithm in more details. In this slide, this algorithm is shown. First of all, at the first step, full color digital image. At the first step, the full color digital image is processed using color space transform. And instead of RGB components of the digital image, we obtain chroma and luma components of this data. Next, we apply the core of the algorithm, which is called discrete atomic transform. This discrete data transform is based on special type of atomic functions, which are compactly supported solutions of functional differential equations with constant coefficients and linear transformations of the argument. Next, that coefficients that were obtained previously are quantized using the standard image processing technique. And finally, the quantized data is encoded using a combination of column codes and binary arithmetic encoding. And in this research, we are going to improve the last step of this algorithm. So it is clear that if we want to improve performance of some algorithm, for example, image compression, we can improve, for example, the last step, providing lossless compression of the quantized data, and in this way, perhaps we can obtain, we can get better results. Consider column codes in more details. In this slide, we can see some examples of column encoding of integers. And in general, the following formulas are used. So each positive integer is represented with several number of ones after the 0. And by the way, this 0 bit denotes the stop of binary stream. Yes, for some integer, and in the same manner, each negative integer also encoded. And we suggest in this research the following. We suggest another type of encoding of quantized data. So we represent each integer with the following approach, and then we apply the following bypass. First, we scan the first bit of each value. Then we scan last bit of each non-zero value. And finally, we scan all other bits of each non-zero element. Maybe one can say that it's too complicated, but let's consider the following example. And this example illustrates the proposed idea. So here we should encode some set of integers. We represent them using the proposed approach, and after that we scan these bits using the following approach. First we scan the first bits, after that we scan last bits, and finally we scan all other bits. In this way we obtain binary stream, which is compressed using context adaptive binary arithmetic coding. And the main question is, so is it better? So we have proposed some idea, and let's prove that this idea works. And the main aim of this research is to show that the proposed coding scheme is better than the previous one. In order to show this, we propose to use the following classic image processing indicators. First, we consider compression ratio, and also we use two distortions measures, root mean square error and peak signal to noise ratio. Also, in this research, we use very specific data set. We consider a set of high-resolution satellite images of the European Space Agency. The total amount of the data set is 93, and raw data requires more than 7 gigabytes. And this data is very specific. Consider this very specific example. We can see a small copy of typical digital image from the considered data set. And if we consider its true size fragment, we can see that it contains a lot of small details and sharp changes of color intensity. And in this research, we use the following test data processing procedure. We compress each test image using discrete atomic compression algorithm. After that, we compute compression ratio, and also we have varied quality loss metrics. And finally, after we decompress each image, we compute metrics of root mean square error and peak signal to noise ratio. And we have got the following results. This table shows these results. As we can see that the previous approach is not so good as the proposed one, but maybe these numbers are not so informative. Let's consider the visualization. By the way, this table contains two parts. Yes. And if we visualize our results, we can see the following. First of all, rate distortion curve corresponding to the proposed approach, which is called progressive coding, is we can see that this curve shows that the proposed idea works. And also we can see that total memory expenses which are required using the proposed idea is less than the previous one. So we can see the following. The following results can be stressed. So progressive coding provides high compression ratio. Yes, in combination with then a combination of long codes and algorithm TABAC. Also, the difference is not so high, and we can see that this difference decreases as quality increases. And also we can see that for high quality measured by PSNR, the proposed coding scheme ensures minor increase in the algorithm DAC performance. And now let's consider the principal features. And the principal feature is that our proposition transforms just the last step of the algorithm DAC. And for this reason, all features of the algorithm DAC are provided. So linear time and spatial complexity is provided. Also, image encryption feature and machine learning oriented data format are also provided, since they are provided by the discrete atomic transform. And discrete atomic transform step remains without changes. So, as a conclusion, we can see that The proposed approach ensures better compression provided by the algorithm DAC, and also we can see that less arithmetic operations are required, which is of particular importance when we have low computational resources. And also, the proposed idea preserves low resource-intensive image processing and encryption features. Dear colleagues, thank you very much for your attention. Let me answer your questions.
Thank you very much for the presentations.
Okay. Are there any questions?
I have short questions, if I can. You mentioned so-called machine learning ready format.
I'm really sorry for technical issues.
Do you listen to me here?
Yes, we hear you.
Yeah. You mentioned machine learning format. Could you please describe it in more details? What do you mean here? Thank you.
Colleagues, can you hear me? I'm sorry.
Yes, we can hear you very well. And did you hear the question from Andriy Shelist?
It was about machine learning data representation, yes?
Yes.
So the main idea is that, okay, so thank you for your question. So the main idea is that data is discrete atomic transform coefficients are grouped into several blocks. And the first block contains the small copy of data, and all other blocks contains data that provides better representation. And we can analyze not just the raw image, not the whole matrix of the image, but the discrete atomic transform coefficients in order to obtain some machine learning results. So we can use, and the main idea is that image should not be reconstructed. So, for example, if we compress digital image using JPEG compression algorithm, and if we want to apply some algorithm and use this image maybe in convolutional neural networks, we should decompress this image. And our idea is that we can use that coefficients without the whole data reconstruction. And that's and this feature we call machine learning data-oriented format.
Okay, thank you very much. And maybe one more question. What is the domain where this coding algorithms is the most efficient? Where do you recommend to use it for which kind of imagery or? What is the area of applicability of the algorithm? Okay, so I think there is some problem with connection.
I think there are,
there is some delay, maybe, in connection.